All right, welcome. Today we are diving into something pretty amazing, the world of small-angle X-ray scattering, or SAX for short. We're going to find out how scientists are, quite literally, seeing the unseen. So let's just start with a simple question. Have you ever really thought about what gives a plastic water bottle its surprising strength, or what makes a high-tech fiber so flexible? Well, the answer is something you can't see at all. It's an invisible architecture, a hidden world where molecules are arranged in these incredibly specific ways, all on a scale that's way, way smaller than your eyes can possibly see. So that's the big puzzle, right? How do you see an invisible world? That's exactly what we're going to dig into. We're going to look at how scientists study the hidden structures that define, well, pretty much all the modern materials around us. To peek into this microscopic world, normal light just won't do the trick. You need a special kind of flashlight, a really, really special one that uses incredibly powerful and precise X-rays. And that brings us to the star of our show today, SAX. You can think of it as our nanoscale flashlight. It shines a light on what scientists call the mesoscopic scale, this weird in-between world that's bigger than individual atoms, but way too small for a regular microscope to ever see. So what makes SAX so special? Well, let's put it in perspective. Other X-ray techniques are fantastic for looking at individual atoms, the tiniest little building blocks. But SAX, it kind of zooms out. It's built to see the bigger picture, how huge groups of molecules are arranged over much larger distances. It's really the difference between seeing a single brick versus seeing the pattern of the entire wall. And that's the key. SAX is the technique that bridges that gap. It uses those X-rays to reveal how big groups of molecules, like long, tangled polymer chains, are actually organized. It gives us a map of that invisible architecture we were talking about. Okay, so we know what it is, but how does this thing actually work? Let's take a quick, simplified tour of a SAX beamline. And trust me, these are some seriously powerful instruments. It all starts with the light source, but you need an unbelievably intense and focused beam of X-rays. This usually comes from a massive machine called a synchrotron, which basically whips particles up to nearly the speed of light just to create these super brilliant X-ray beams. Now, after that raw beam is created, it has to be refined. It gets passed through something called a collimation system. You can think of it like the lens on a really good flashlight. It uses these tiny, perfectly lined up pinholes to focus the X-rays into a superfine, razor-sharp beam, getting rid of any stray light that could mess up the measurement. Okay, so finally, that superfine beam hits our sample. The X-rays bounce, or scatter, off the structures inside, and a detector on the other side captures the pattern that they make. Now, this pattern isn't just random noise. It's a unique fingerprint of the material's inner world. And by analyzing it, scientists can work backwards to map out that entire invisible architecture. So, we have this incredible tool. What can we actually do with it? Well, this is where it gets really, really cool. Let's look at what SAX reveals, because the applications are just stunning. Everything from creating next-gen materials to unlocking the secrets of life itself. Check this out. This is fantastic. On the left, that's a real SAX pattern from a muscle fiber. Now, it might look a little abstract, but it is packed with information about how the protein filaments inside are arranged. And from that data, scientists can build a super detailed 3D model, like the one you see on the right, to figure out exactly how our muscles contract and generate force at the molecular level. And its power isn't just for biology. SAX is a total game changer for material science. Here, you're seeing scientists aiming the beam at a polymer fiber as it's being spun. They can watch live in real time as the molecular structures form and line up. This means they can tweak the process as it happens to create materials that are stronger, lighter, and more flexible than ever before. Honestly, the applications are just exploding. With SAX, we can design brand new polymers, we can watch materials stretch and even break in real time, we can study how complex things like proteins fold themselves into their perfect functional shapes. You can even watch chemical reactions as they're happening. It's all leading to new and improved materials for basically everything, from airplanes to our electronics. So, this all brings us to the big picture, the future we're building. And it raises the question, why does seeing this unseen world truly matter? It matters because by seeing the unseen, scientists are no longer just discovering materials, they're actually designing them from the atoms up. From creating new medicines that can target specific proteins to engineering smarter, more sustainable ways to manufacture things, Sachs is literally providing the blueprint for the future. And really, that's the takeaway. This technique gives us this incredible, unprecedented ability to build our world from the nanoscale up, which leaves us with just one final, very exciting question. What will we discover next?